those going. We're done with this. Oh, yeah, I wanted to go through. So this, let's see, it's 10:10. I brought some of this. What was that? That one, like escape. That's pretty weird. Escape looks like it's a bad thing to press here. Oh, and I never hit this. Ejector's not working. It's warm enough or something. Oh, we can get by with one. Yes. All right. So, oh yeah, the PVME. So, what's some of this PVME in here? I wonder if everyone knew we didn't have President's Day off. Some people are taking it off here. Okay. Duck cam. There wasn't much traffic coming in either. So anyway, this is an LCST, so temperature and composition. And then as you heat it up, it phase separates. Something like that. So this is, let's see, where does this happen? It's at like 20–30% polymer, I think. And then this is two phase. This is one phase. Hey, and then this polymer is PVME has this methoxy group on it. And so, so basically this has like del minus, and you have water, have like del plus and water. And that can associate with it. And then as you heat it up, that is so normally that would make it miscible. And then as you heat it up, that association breaks down and it becomes immiscible. But this happens at right at your body temperature. It's like 90. So that ends up being like 60 C, I think, or something. Or let's see, 40 C. Like that. Right? I don't know what body temperature is in centigrade, but anyway, so this is that PVME is a dilute one. There's so these are probably like, this is like 5–10%, 5%. This is probably 15%. That one's like maybe 40%. And this other one is like pretty high concentration. So like you can hold it in your hand and it'll phase separate, but it'll follow that curve, you know. So we'll have like, it'll take time too because it has to reach temperature. So we have like a sample here, one here. This one's questionable. The other, there's 4. So it's something like that, basically. We have one that's like 70%. There's one that's actually this is really 50%. So they're all like in here. they sell it, when you buy it, it's at 50%. And then these are diluted down. So they supposedly one of these, the medium one, like this one will phase separate easiest. So anyway, the goal is to like hold this in one of your hands and like see if you can get the phase separate. So it'll go like white. You can rotate. There's only 4. You'll get rid of that. So I'll give you one later. Well, if somebody fails, then it has to reach your body temperature and it'll phase separate. So it'll just be like milky white. That's the goal. All right. So anyway, so that's kind of an example of this phase separation thing. This LCSD idea. So just so you can kind of believe that it exists. And again, like to get that, you need to have the A has to be positive, and then B's negative. So as B causes it to mix, when the temperature goes up, B diminishes and it doesn't mix anymore. So normally chi just has a B by T term and B's positive. Here B's negative because B positive means that it leads to phase separation. B negative means that it mixes. So when B's positive, normally you want to have phase separation happening with the entropy term, because entropy would drive mixing. So anyway, so the signs matter here. So there's that thing that's in the notes, kind of stuffed in here. That's actually PVME, right? So, and like Post-it glue is polyvinyl ethyl ether. So if you have 2 CH3s here, that's the glue on Post-it stamps. It was like, I think the story is it was a chemist made the stuff at 3M. And then like he left it around or something. The secretary figured out that she could use it for this Post-it thing and started using it. And then they figured out that could be a product. You know, so it was kind of discovered by accident. Anyway, this stuff is just kind of gooey. You know, it's gooey polymer. So, all right. So this is the collapse thing. So I wanted to go through that. It's a little bit. So this might not be the only story, like how to describe the collapse thing, but anyway, this is the way Grossberg described it, and I think it's the theory that's commonly accepted now. So there's that book, Giant Molecules, you can look at it if you want. And then it's also in the Colby-Rubenstein book on polymer physics. They go through this too. So Grossberg, I mean, the more you look at it, there's kind of a couple cheats in it, but I can point those out. But in the end, you get this behavior. So in the end, this is what you want. So let's see if I have that in here. I don't. All right, so you have a cubic equation, like, or you can have and then that's basically n over v RT, and then we say you can have v minus b n RT, and then you add in the term that makes the pressure drop, so minus a over b squared. So that means 1 over the density there. So basically this is binary interactions. This would be ideal. This is excluded volume. So if you rearrange that equation, you end up with a cubic expression. So you can write it. One way to write it is P equals density times RT plus some parameter B times density squared plus C times density cubed. And you can go on, and it's called a viral expansion. If you do these in derivatives like dp dt or dp d rho, then that's a Taylor series expansion. But if you don't do that and just call it ABC, then that's a viral expansion. So it's the same as a Taylor series kind of. Except Taylor series has the derivatives in it. Anyway, so if you do that, and then you take this expression, the van der Waals expression for non-ideal gas, and you force it into this viral expansion, you find out that B is the excluded volume minus A by T. Okay, so that's excluded volume. This is an attractive interaction that causes a liquid phase to form from a gas. So you don't have an ideal gas anymore. You think if you form a liquid, then it's temperature dependent. Right, so as you cool it, this becomes negative, and then that makes the pressure drop. When you get to a transition point where I think T equals whatever that would be if that was 0. T equals B over A, I guess. Now T is A over B. That's your star T, which would be, for us, that would be the theta temperature. Okay, so this, believe it or not, you had in chemical engineering thermal, right, and in every other thermal. The viral expansion, and I'm seeing a lot of faces like, what? You know, but you definitely had this now. So anyway, so you can work this out on your own to go from this to that to this, you know. So basically this setup, this is called a cubic equation. And if you plot that, so PV would be like energy, so we can get an energy expression out of this. It's a cubic expression. It's got density squared in it. Right? And if you plot that in the two-phase region, it's going to have this squiggly line behavior, right? Where at a given temperature and then volume, then you're going to have like 3 roots, right? And then there's these zones here. So let's see, this is PV and this is added T. It's isotherm. Sorry, P versus V isotherm. That's why I needed to have the picture of this going by memory. So the Maxwell equivalency is when you have this area equals that area, then you're at equilibrium, and that gives you the 2 phases that are in equilibrium. And this is the root that you don't use. In other words, if you know the P for a given T, then you have 3 roots. One of them is garbage. One of them is like this low volume one is liquid. The high volume one is gas or vapor, right? So that's a liquid vapor equilibrium. And it's called a Maxwell construction. To take those areas, you can also do set the derivative of this, and you find it has 3 roots. The derivative of the energy equation equals 0. You find it has 3 roots. It's just like the standard way to do thermodynamics. This Maxwell construction is like a groundwork brick of thermodynamics. Right? So this guy Grossberg wanted to get a Maxwell construction from Flory-Huggins theory so he could predict coil collapse. Right? So he does that by including the C term, this third viral coefficient, which is kind of odd because B already has phase separation in it. In other words, B, the reason to include the A term in the Maxwell, in the van der Waals expression for B is to have, so you can form a liquid phase, which is a collapse. That's a critical point. So you already have a critical point without, and that gives us the chi parameter. Like the chi, that gives us the theta temperature, right? In other words, for polymers, this B is going to be 2 times 1 minus 2, or 1/2 times 1 minus 2 chi. Right, so this 1 minus 2 chi gives you the chi C, which will give you, since chi equals Z KT, so Z delta E over KT, and that gives you this critical temperature, which is called the theta temperature. That's like where phase separates. That's the point on our graph. You do RG versus T, and then it meets that theta temperature, right? Where RG goes in all squared by 6. RG squared, so the square root of that is RG. That's where it meets the theta coil size. And then it goes on further. So that's where it goes on further to form a globule. So you have this thing, that thing, and then it forms a globule. Right, so you have 3 states. So a little wishy-washy how Grossberg did this, but he says in order to, so you can get the theta state with B, but you need C to get this globule state. He invented this. This doesn't exist. No one ever uses C. Like no one else in the world ever used C. Viral, I don't know if Viral, I don't think it was a person, I think it means something, but basically Viral said it was A, B, C, D, E, F, whatever, but no one has ever used anything but B, the second virial coefficient, right? So anyway, so he picks up C and says that he can predict a Maxwell construction if he includes C. And he can, he does, with a little bit of hokey pokey kind of weird thing going on, but he does it. So that's kind of satisfying. And then people found out that, so you can see this is his Maxwell, it's the same thing. It's a quadratic equation. It's got 3 roots. This is the free energy. This is alpha is the coil expansion, so the coil size versus the theta size. And then 1 would be the theta temperature. Then below 1 means he's coil collapsing. And above 1 is the expanded coil, kind of like the single phase. Then he's got this other parameter X and Y. X is kind of B and Y is kind of C with some other terms in it. So that's kind of the idea of what he does. These are ISO Y terms, ISO third virial coefficients versus the B, which would X, which would be kind of 1 minus 2 chi. And then so X can go negative or positive. Generally, this would be the theta temperature when X is 0. And then negative X would be expanded coil, and positive, let's see, negative X is collapsed and positive X would be expanded because X is 1. So this is where the sign thing comes in weird. So if X is B and B is 1/2 minus 2 chi, and chi is like the A term from the van der Waals. So plus A means you're going to form a liquid.
Oh, you haven't changed.
Oh, shoot, sorry. All right, so let's see, I said that wrong. Plus A, so A equals 0 is the critical point. And then let's see. No. The virial coefficient, anyway, the virial coefficient plus means that it's going to be single phase. 0 means critical, and minus means it phase separates, but that means that chi is B is minus chi. Then minus chi is single phase. Chi is 1/2 is when this be 0. And then positive chi above 1/2 is where it's phase separating. So the signs are different, and there's a half thrown in to confuse it. So the sign of all this stuff, you have to be pretty careful about it. He says that B is typically positive, which would mean that we have miscibility. And then he says C is typically negative, means that C drives immiscibility. That's no one has ever said that before, okay? But he just says it. And this can be interpreted, this expansion can be interpreted in different ways. One way, this is squared because it's binary interactions. And this is cubed because it's ternary interactions. It's like, how does number 1, when it affects 2, affect 3? That's a ternary interaction. Like 1 is attracted to 2, but that might make it not like 3. Or 1 is repulsed from 2, so it drives it to 3, something like that. So it's got to be like a 3-partner impact thing. Or these things can just have to do with geometry. Like this is for first term would be for spheres. That would be for thing that has one kind of asymmetry, and this thing would have like curvature too. So in colloids, they include the other terms to account for structure. So you can use these powers to mean 2 different things, at least 2 things, probably more than that. One is like the order of the interaction, the other is the shape of the object. So whatever that's worth. So this people spend a lot of time talking about. That's why it's in the book, the undergrad book. It's like van der Waals and then viral expansion, and these are like the doorways to get into all kinds of complicated things you want to talk about. Right, so you can kind of. It takes a little bit to figure out what's going on, and I'm not sure I've even ever really fully understood what's going on. Yeah, but basically, at some point you have to trust Grossberg. So what he does is, first thing he does is he redefines alpha. So we had here. So the way Fleury defined alpha was pretty simple. First he had C infinity. So he said C infinity was R squared over R squared, where this R squared was the chemical unit and kind of the step length of the chemical unit. Right. And this is your actual unit, and then the step length of your actual unit, which is a Kuhn length. So this is a Kuhn chain. Right. And then we said that NC LC is going to be the contour length, and that has to equal N real L real, and that means R squared by R squared is the real Kuhn length divided by the chemical unit step length, which is 1.54 angstroms for carbon-carbon. It's the same thing as the wavelength for copper K alpha radiation, which is a common one used for diffraction, which is really odd. So carbon-carbon bond length is the same length as the copper K alpha radiation they use for diffraction. Really weird. It's a coincidence. And so anyway, so it makes it easy to remember, I guess. But anyway, so we got that. That's what this C infinity was, characteristic ratio. And affinity means that we didn't look at the n groups, right? About n groups. So then Fleury said, okay, if I put that chain and I have an R in the theta condition, and then I go to an expanded coil, and then I'm going to have a coil expansion factor. I'm going to call it R expanded coil squared divided by R theta squared. That's Fleury. That's called a coil expansion factor. You can see it's just the same as a C infinity. It's just kind of talking about this thermal transition business, right? Instead of this kind of business about the Kuhn length. So then, but Grossberg doesn't do that. Grossberg says this is alpha squared. So his alpha is just R over R. And that makes it easier because then he can say he's going to do like derivative of the free energy as a function of R. The R, set that to 0 when he reaches his magic R, and then you can solve for what's the coil size at that point, instead of trying to solve for this R squared thing. So, but it means that what he does doesn't match up with any other book. And it turns out when he does that, so when we got the 3/5 scaling law, we had to make some approximations, right, to get that. You could integrate it and get 1.72, or you could make some approximations like infinite coil size, and then you could get the 3/5 law of it, right? So anyway, he can get that 3/5 directly with no approximations if he uses this alpha. So what he does, he takes the whole, so this is his picture from his book. So this is a simulation. This is kind of, I guess, reality. That's what an expanded coil looks like, and good solvent. This is a theta coil. and this is the collapsed one. So the sizes change quite a bit. This is, I mean, it depends on the molecular weight, but basically the sizes change a lot, right? So that's what he's trying to emphasize here, is that there's big changes in size. And you could see that from that plot, this plot too, that you have, I don't know, it's 2,700 and it goes to 1,000, you know, so it goes down to 500. So it's a factor of kind of, did anyone get a separation? You did? All right, that's pretty good.
Yeah.
Great. All right.
A blob in there.
Nice, sweet. Okay, anyone else get it? I know, well, if you're at the different parts of the phase diagram, everyone's about the same temperature, you know, so basically, so you got it too in the back, right? And did you get it? Oh, all right. So, but you guys didn't get to do it yet, huh? We have to let it cool down a little bit, just to see the phase separation. All right. Oh, that's good. All right, this one's already separated. This one's cooled down. So it's clear when it's single phase. It's called a cloud pulse, right? Because it's cloud. Yeah, that is pretty well. Yeah, it's more concentrated. So we're going, so hold it, you have to hold it in your hand and let it. You can just do one. That one's already separated.
It's not gonna separate.
It's not gonna do anything.
You never know. It could be like have another one up above, but. All right, anyway, so. All right, so all right, so this is what he did. This is the expression we had before. Just we divided by our cubed and the chi term, and it's got, this is b, this is our second viral coefficient, the b. And then this one's got r squared up here and z's down here. So the n dependence is like squared and 1 over. This is the entropy term. So that's the ideal one that comes from comparing the so that one comes from comparing the let's see, we had the energy of a chain. We had the 3/2 r squared over nl squared. Then we had exponential minus ke activation over kt. So the Boltzmann. This is for the coil size, and then this is for Gaussian, right? And then we just compare those two, and we get the energies 3 kt r squared over 2 nl squared. Right, that's our basic number one term. So 3/2 r squared kt over nl squared. That's our energy for an entropic chain. Then we added this enthalpy term to it, and then that's got 1 over r cubed, so r squared. So when you do the alpha substitution, you're gonna get 1 over alpha cubed, and this is going to be alpha squared. And then you figure out using that expression to substitute in to get what all the other constants are, and you substitute that the b term, you use the second viral expansion, so that's going to be 1 minus 2 chi. So you have 1 minus 2 chi here. You just put in b for it, and kt. The z's, because this thing has a z in it. So since the chain has a fixed molecular weight, and the only thing that's changing is the r, the size, then you say these terms are constant, like everything else is constant here, except that b depends on temperature. So we're not going to minimize this with temperature. We're going to minimize it with r, size, right? So you take the derivative of that expression with respect to alpha, and you get a unique solution. You don't need to do any extrapolation. You get exactly this equation, which is the Fourier-Krigbaum expression. So Grossberg's approach using this alpha thing, which kind of confuses things a little bit, actually leads to a cleaner solution. Like he actually gets the solution, which we know isn't really the right solution, because we know it should be 1.72, right? But this 3/5 is kind of what people use. So you have c to the 1/2 to the 1/5 is 1/10, right? So you have c to the 1/10, and then alphas r by r, and then R is Z to the 1/2 times L Kuhn. So, oops, sorry. All right, so his expression is alpha Z to the 1/10th, and then alpha has a Z to the 1/2 here, so you have times Z to the 1/2. And when you multiply, you add the powers, and 1/2 is 5/10. So 5/10 plus 1/10 gives you 6/10, which is 3/5. Right. So that's the 3/5 power comes out of this thing. Works out. So this part, there's no, I mean, he does find out there's a simple way to directly get this 3/5 power. So that part's pretty clean. It's kind of nice. So then you get the 3/5 power from that. Then he comes in with this deal. So we had the other part of this is 1/alpha cubed, right? So, and that's got the B term in it. So that's going to be this UA, the enthalpic part of this expression for free energies. You've got an entropic part, the ideal case, and this enthalpic part. And then that's got a, if you work this out, it's got a Z here. So, oh, N is the density, right? N is the coil density. So actually you start here. So this is written backwards. So this is that term, right, with the alpha cubed. And then you say, if you want to have density squared, that's going to be n squared divided by r cubed, r to the 6, because it's going to be n by r cubed is n by v. So you have n squared by r to the 6 gives you the density. So he's got z squared by r to the 6. That's the density. That's the density squared. Right, and b times the density squared is the second virial coefficient, so it's got to have z squared by r to the 6. He plugs that in and wiggles the alpha around. He ends up with an r cubed at top because he only had an r cubed here, so it has to be r cubed to get it to work out to be density squared, and then r cubed is the volume, coil volume. Right, like I said, this gets to be kind of, you know, and whatever, but basically. That's his viral term. I mean, this is a viral term here. That's kind of clear-cut viral. Once he has that expression, he takes that out front, and then he just adds in his C term, which is a third viral coefficient, is some number. Right. So B and C are both temperature dependent. B is positive. So if it's in the single phase region and chi is above 1/2, then B would be positive. B would be somehow B would be positive. No, chi would be negative, right? Below 0. That's single phase. Then it's 1 minus 2 chi. So you'd end up with a positive B to be single phase. That's how it works out. So anyway, the classic thing of viral coefficient is that it's positive, and that means single phase. 0 means that it's at the critical point, and then negative means that it's phase separating. And 0 isn't actually a really hard and fast because there's some shift term, and in this case it's the 1/2. Like the 1/2 has to do with whatever is left over somehow. So there's some other entropy part of enthalpy that you have to account for that makes it not 0. But theoretically, it would be like B0 is the miscibility limit. Right, so anyway, B positive, that means miscible, and then C negative means you can get this transition, right? And then it's n squared n cubed, so that's his expression for U. He just ad hoc threw in the C term. The rest of it, this thing can be gotten from the original entropy thing here. This is too involved to go through, you know, in some ways, I don't know. Anyway, it gets worse. So then he introduces this idea of a blob, which is like already exists, but basically he's saying that when you heat it up, it's going to coil up locally. So it's going to make it's not going to be an instantaneous shift to the globule, or it could be, but it probably doesn't have to be, right? So order to go from this to that, he's going to make blobs in this that are that. And then it's going to make a Gaussian chain of those blobs. And then with that kind of idea, he can kind of say like how many of those blobs, the same thing that was done with the other blob models. And then he can get an accounting for the entropy of the blobs. So the idea is like the blobs. Anyway, the idea is that the blobs, so you have a chain made up of these blobs. Each blob has like KT energy. So it's like the number of blobs, which is Z divided by this G star times KT, gives them an entropy. That gives like an entropy term that has to do with this kind of collapsing chain. And eventually this will go to 1. The whole thing will be a globule. And that will be the smallest translational entropy it has. And then this G star is alpha squared, because it goes NL squared is R squared. And G is kind of N, and then alpha is R, so it ends up being 1 over alpha squared. So that's where he gets that. So in the original one is alpha squared, and this one ends up being 1 over alpha squared. Or the original one's, let's see, the original one's 1 over alpha squared. This one ends up being alpha squared. So you get this kind of new entropy term that replaces that one, like the original one, whatever that is. This 3 alpha squared term gets replaced by alpha squared, 1 over alpha squared. So that gives you this shift, like alpha of 1 means you're at the theta condition. Alpha above 1 means you're expanded, and alpha below 1 means that you have collapsed. So that means that one of these terms will dominate in the 2 regions. You have one kind of equation to rule them all. So basically, if alpha is big, then only the squared term matters. If alpha is small, only the -2 term matters. And in between, you have kind of transition behavior that you can model the collapse of the chains. It's kind of an okay thing. So, I mean, it's a little bit kind of wishy-washy, and he's throwing in terms all over the place, right? So anyway, there isn't really a better explanation. So I think this is probably as good as it's going to get. It's like if you look at the Flory-Krigbaum, what they did in the 60s, it's so clean cut. Everything is like boom, 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 boom. And then here's the answer, and it matches the experiment, right? In this case, this collapse thing is a little bit like, was it a first order transition, or was it a second order transition? How do you measure that? How do you prove it? So there's a lot of wishy-washiness to it, and the theory is also not as firm. So basically, you could kind of question what's going on here, but he ends up with this expression for free energy. It's got his B term, his C term. So this is kind of the miscible term. It's positive. This is negative, kind of the immiscible term. Ternary interactions, binary. And then because it collapses, he has to account for the entropy of these blobs that form. So he accounts for that. And he also still has the coil entropy term. So he's got 4 terms in this. And he can take a derivative of this with respect to alpha, like he did to get the Flory-Krigbaum. And then he can get a messy, kind of a messy expression, right? So in order to make it simpler, quote unquote, he invents these X and Y terms, which are functions of basically B and C. So X is B, Y is C. They have some other terms in them, including a K term. There's K1 and K2 terms. So basically X is B, Y is C, and he has this kind of expression. He says that if he's in the collapse, then this alpha -3 and the X term dominate over these two. So alpha is going to be much smaller than 1. So these 2 terms go to 0. Then he just says this, he can equate those 2, and then he can solve for what R is under that condition. So ignoring the left-hand side, just taking the right-hand side, you can get an expression for R, and X is B, Y is C. So it ends up with C over B is the governing thing. So the third viral and second viral decide what kind of coil you have, and then the lead term is that you have a 3D object. Z is 1/3 of this thing. So the Z is 1/3 is something that he wanted. And then he has these two terms to play around with to see how this behavior acts. Like how does this alpha change when he changes the conditions for C and B? B is basically temperature. C is something else. It may have temperature in it. So C again isn't really defined here. C is just some number, you know. So anyway, so that's how he gets these maps. He takes that expression for R, then he can get alpha, because alpha is R over the theta R. 1 is where it's at the theta condition, and then he's got this behavior that's quadratic. And he can kind of do the Maxwell construction where he equates, so you draw a line at fixed X is B, B is chi is temperature. So you do an isotherm would be like across this, and the other one's iso C. He's going to like different Y's. So you can find a point where you can do a Maxwell, you can get the areas of the two above and below the line are equal, and he says those two phases are at equilibrium. So at that point, he has a first order transition between small r and big R, or big R and small r. He has a coil collapse, like protein folding. So he has one condition where you can get protein folding, and then in the other part, he still gets some kind of transition in the top curves, but it's a second order transition. So when he has the quadratic, so this 3 roots, he's got a first order transition, and the other one's a second order transition. So he's happy. That's what he wanted. He wanted to see synthetic polymers go through this collapse as a second order transition. You know, in other words, going from theta to collapsed, and it's a continuous thing in temperature. It's not like a step function. Right. So first order would be a step function. This is a second order. Right. And then proteins will show like, boom, you get to the right temperature and it folds. I mean, in a really coarse way of looking at it. Right. In other words, if a chicken was a ball, kind of thing. So, I mean, but it's so, because it's really like, there's so much complication to folding. I mean, you think about I was talking about the what is it, chromatin or something. There's like a protein rod and the things coil around it, and then like it's all compacted down, and then it'll unfold a small piece and read it. It's like what that has to do with this. I mean, it's pretty questionable. But you do have, and also the folding process is like all kinds of other proteins that assist in the folding. So it isn't on a direct energy. It's like catalyst almost. And it's almost like one molecule comes in and holds a part of it and makes it possible for it to kind of fold in and meet the other part. And then that thing goes away. Right. So they know some of the details of it, and it's not like this. It isn't like a first order transition like that. It's the denaturing could be, like when you denature a protein, so you cook the egg or you make you whip the milk and make whipped cream or something, so you're denaturing the protein, the coils expand. So that could be kind of a first order transition like this. But to make it go back, you can't take whipped cream and make milk of it again, so it's done. So it's not a thermal reversible process. Anyway, so nonetheless, that's the theory. That's kind of the theory that goes with this. So it's more involved in in this experiment. I didn't go and get these papers are on the web page somewhere. Oh, there's a link to it here. If I just figure out how to do it, that looks like it's a link. Maybe if I do this. Right. Nope. Anyway, these papers are on the web page somewhere. Basically, they make these two different polymers. So one of these penny PAM is kind of like a cleaner PVME. It's a similar kind of polymer. It's got a phase transition also at body temperature, just like this in water. The difference is this PVME mixes with polystyrene. So it's rare miscibility with polystyrene, and then it'll phase separate from polystyrene if you heat it up to like 70 C. So penny PAM doesn't do that, right? But penny PAM has some interesting things because it looks a lot like a protein, like it's got a amide kind of linkage here. So it's a biocompatible vinyl polymer. So you can make it in a bucket with a free radical, and it looks like a protein on the side chain. So it can bond with, do hydrogen bonding. Like this unit is a plane, like a deck, like a card, because it's, anyway, this part of it's like a card. It's flat. Then this little antenna stick off. So you have this kind of rigid side unit that hydrogen bonds. Anyway, this also has an LCS2 with water because it can obviously hydrogen bond in two ways. Like you can do a negative hydrogen bond partner or a positive hydrogen bond partner. So it can actually bond with itself too. Right, so anyway, so then you can kind of shroud off the positive part by making it a ternary amine, right? And then all of a sudden the behavior shifts. So this one has a first order transition. This one has a, or this is first, that one's second. They both do an LCST in water. And you can kind of map out what's going on in them. You can kind of look at this behavior in terms of this A and C thing of Grossberg. Right. This is something that people use quite a bit. So that rate of gyration, I'll show you like this week probably. You can calculate the rate of gyration directly in terms of the end-to-end distance. It's a square root of 6 relates it to. And then the hydrodynamic radius is the radius of an equivalent sphere in terms of viscosity. So if the drag coefficient of a molecule, if it was a sphere, and what's the radius of that sphere? That's the hydrodynamic radius. Right, so if it's a 3D object, RH is R. Right, and the rate of gyration for a 3D object is 3 square root of 3/5. So it's smaller, right? So your square root of 3/5 is the ratio of these two if you have a sphere. That's down here, which if you look at the numbers is like whatever this number is. Right. So I don't know what that number is. I don't remember. Looks like it's 0.9 something, right? So that's a sphere. Oh, it says over here, draining sphere, 0.92. That's what it is. Sorry. And then funny thing is that when you get a coil, RH gets smaller and RG gets a lot bigger. Right, so it's square root of 6, so it's 2.45 times R, and this thing's going to be some fraction of R. So then all of a sudden you get, for expanded, that ratio goes to 1.6, and you can calculate it for a theta coil 1.5, sphere is 0.774. So basically, you can get this measurement from dynamic light scattering, you get that measurement from static light scattering. So the same machine, you can get those two numbers. And you can kind of say what it is, as a function of going through this thermal transition. So temperature is the bottom axis. You can see like it goes to a 3D object. It's an expanded coil. Then there's this little nib thing that happens, right? So protein people are interested in that nib because it means that the thing's squirming around and it gets actually denser than the native state for a little bit. So it's this wiggly loosey thing, and then it's starting to do some kind of shrinking, and it gets really small, and then it poofs out into what it's supposed to be. And then it's perfect. It's almost like I don't know, there's things like toys or something where you fold it and then it pumps back out to be where it's going to be. I don't know. I've seen it somewhere. I don't know exactly where, but that's kind of the behavior they're seeing in like protein folding, and they're claiming that they see it with this kind of simulated protein structure. It's like a poof back out to the native state thing. Whether that's real or not, who knows, but basically they're doing that kind of thing. This is from a while ago, it's like 1998. So you notice like there was money in protein folding like in the 1980s, and then the money disappeared, and then it all went into like specific disease studies. So if you weren't doing, so for a while, there was like a heyday of protein folding. And everyone was pretty excited about it. And Grossberg and the Russians were coming up with these theories. Then like all of a sudden the money just like disappeared. So we had one of the guys was I forget his name. I think it's like Dole or something, Doll, but he was at San Diego, that institute there. And he did a lot of the primary stuff on protein folding. And then like he came to UC and gave a talk about like 5 years ago. And it was all about like MEMS devices. And someone asked him like, why aren't you doing like the thing you could have won the Nobel Prize for? And it was like, he basically said like, there's no money in it at all. So the money completely left that field. So there's a lot of these like legacy studies of folding. You know, it's still important, you know, Alzheimer's and stuff like that. It's kind of governed by this stuff, but in cataracts in your eyes and things. But there's a bunch of protein folding problems. There's also issues about 30% of the proteins aren't natively folded, they're natively unfolded, and they know nothing about those. So they kind of know about the folded states, acting like a key for chemical reactions of reporting other nucleic acids around or something. But there's like this whole 30% of all the proteins that they're just floating around and doing their stuff without any kind of specific structure like that. You know? So there's some interest in that, but only if you can like link it directly to a disease like Alzheimer's or something, and have like actually a treatment pathway. Like they want to see like animal studies. They don't want to see like someone fiddling around with a theory of folding or something. Right, so anyway, so there's that business. So that's why that's kind of somewhat of a buried topic. Like you still find papers on it, but it was really popular for a long time, like 10 or 15 years, and then just basically totally disappeared when some kind of political thing happened. So and then it's still like popular in Europe. Yes, like different parts of the world, but basically not in the US, you know. So anyway, so don't plan on doing that. So the next thing is just to go through any questions on that stuff. Next thing is to go through like kind of some kind of scattering things, and basically this ratio gyration, how you get that square root of 6 rule. And then we'll go through some scattering stuff about how you calculate this viral coefficient. And what else? The Bayes function for a polymer coil, some of the scattering stuff. There's a bunch of scattering stuff coming up. In a nutshell, what correlations look like, correlation function. And then we'll go over to do some, and then basically we're looking at like techniques from here on out. Like scattering is one technique, viscosity, solution viscosity. Someone wanted to see DSC or something early on, right? So maybe we can do that. So just do, basically there's a bunch of techniques to look at, like what people measure, you know, and how that fits in with things. And that's probably what we're going to do. I think that's the way I remember it. Anyway, all right. So that's about it today, I guess. There's no any questions on the homework or anything? No? All right. Okay, that's a good thing. Usually I get some emails and like over the weekend, but I kind of get the emails. I don't know how it's going on. Oh, thanks.